Okay, I think we can get started. Good afternoon. We'll still have a few more people. Hi, my name is Gaiman Yi. I'm the Technical Director of the i4energy Center. Welcome everyone that's here today and also on the web to today's i4energy seminar. I guess before I introduce today's speaker, I just want everybody to notice that your water bottle is a little different today. I was told these are compostable water bottles, so just about everything else you can compost except for the aluminum foil. And if you feel so inclined, you probably can even eat the bottle, I guess. Okay. Today's speaker is Jim Evans. Jim is a professor of metallurgy in the Department of Material Science and Engineering here in Berkeley, where he has taught since 1972. He was also the department chairman from 1986 to 1990. His research interests include production of materials, particularly fluid flow, reaction kinetics, mass transport, electrochemical and electromagnetic phenomena governing processes for producing materials, which including metals and for storage of energy. Professor Evans has a BS in chemistry from the University of London and a PhD in chemical engineering from the State University of New York in Buffalo. Let's welcome Jim.
It's a great honor to participate in this important seminar series, so my thanks to Gaiman both for that kind introduction and for inviting me to speak. I'm indebted to a number of colleagues, only some of whom are listed here. There are many other students who've participated in this research, and in fact I can see one or two of them in the audience, so they will have an opportunity to assault me afterwards for forgetting to include them. So this work have been going on for a few years, and like much university research, it's somewhat serendipitous. And so my thought was that there should be some sort of unifying theme, and here it is. So when we think about electrical energy, at present, it's largely created at a distance and used immediately. So we think about the electrons that are flowing through the lights above our heads. They've been generated a tiny fraction of a second ago at some plant which is perhaps thousands of miles away. And that's been the ruling paradigm for electrical generation, distribution, transmission for decades. But in the future, it's likely we will have a substantial fraction of our energy generated locally and partly or wholly stored. So that's what the research is about. And it's going to extend from a tiny length scale up to energy scales that are huge. So here's the outline of my talk. I want to talk about printed small-scale thermoelectric generators to start with. Then I'll move on to a somewhat different topic, which is the printing of zinc batteries. And then I'll finish by talking about large-scale energy storage and some estimates of how much that might cost us. So for the small-scale stuff, this is our principal objective, a wireless sensor micro device that's got really four components to it. There's energy harvesting. Some people prefer to call it energy scavenging. Energy harvesting sounds much more genteel, so I'll use that term. It's necessary to store energy, as you'll see in a few moments, and here's a battery that does it and a capacitor that does it, and I'll certainly have a lot to say about this battery, but nothing about this capacitor for this present-day purposes. Then there's a sensor on this thing, and there's one shown here, for example, some piezoelectric benders which have got magnets on their tips and which are capable of measuring the current flowing through a wire, a cable, near which they are placed. And then to complete things, we need a radio to transmit the information and perhaps to receive information which will program features on this device. And this device might be about 1 centimeter by 1 centimeter and 1 millimeter or 2 thick. And perhaps in years to come, they'll be even smaller than that. But this is what we're aiming at for ubiquitous sensing and computing, which I'm sure you've heard about before. So let's talk about thermoelectric generators to start with. And this is a classical picture of how a thermoelectric generator works. There are two kinds of semiconductors, an N-type and a P-type. And you place them between a heat source and a heat sink. And lo and behold, you can generate electricity which can flow through some sort of a load on the outside here. This is what a practical thermoelectric generator looks like. You can buy these things these days. There's a bunch of PN elements in it which are connected in series, and the heat flow is in parallel from the hot side of this device to the cold side of this device. And we can think about using these things to extract electricity from sources of waste heat. An aluminum plant, for example, or an industrial boiler, or an automobile engine, or even the dryer or washing machine in your home. And the temperature differences we're talking about are of the order of about 10 to 80 degrees, depending upon the particular application. So we can think about placing one of these thermoelectric generators somewhere where we need energy for doing measurements of some sort. So let's look at some features of the design and fabrication of thermoelectric generators. And if you look at the voltage output from these things as a function of the number of couples, the number of pairs of semiconductors that you're placing in this device, let's say for a temperature difference of 5 degrees Kelvin, you could see that to get up to a decent voltage, 1 volt is sort of the threshold you need to achieve in order to have practical electronic devices. You need something of the order of 1,000 couples, which is rather a lot, you might imagine. And the area of this device would then be about 2 square centimeters, something of that nature. And so we're going to need in excess of 1,000 couples and that kind of area, and we should be able to generate from that something of the order of about 100 microwatts for a delta T of 5K, which is not very much power, I think you'd recognize. And if you look at the efficiency with which this device generates electricity, it improves with the element length for reasons which I don't have time to go into. So you want something of the order of about 2,000 microns, in length to have this thing work well. So let's look at the ways these devices could be made. So this is the way that large thermoelectric generators, and by large I mean I'm talking about something that's a few centimeters by a few centimeters. This is how they're made at the moment. There are several companies making them. One of them is down here. So you dice these elements from ingots. You place them in arrays. That's labor intensive. It's a manual pick and place, although typically these days that will be done by a robot rather than by a human being. But the result is rather expensive devices. So for a device about the size of a credit card that will generate a watt or two, you need something of the order of $50. At the other end of the scale, there are thin film thermoelectric generators. Micropelt is one of the companies that's engaged in this development. The tricky business is that it's materials intensive, as we'll see in a few minutes. Microfabrication devices limit the height to which we can build these things to about 60 microns. And you can see we need about somewhere between 1,000 and 2,000 microns in order for these things to be energy efficient. So that's not as good as it might be. And right in the middle, we have something we call dispenser printing, which is what we're doing, where we could generate high aspect ratio pillars with a technique that's really a high throughput manufacturing process. So it's a form of printing which is fairly inexpensive. So this is a traditional design which I talked about a few seconds ago. This is an alternative design we call the planar design, which I think was dreamed up by Alex Chen, one of the students, and I think it's rather a clever way of making these devices. So it consists of a P-type semiconductor, N-type semiconductor, metal interconnects here and here, and the whole thing is placed on a strip which can then be rolled up, and the heat flow would then be in that direction. So we can achieve a high density of couples, so a 900 couple, 900 plus couples would occupy a diameter of about 1 centimeter, and it takes advantage of the printing process that we're working on so hard. So think of a substrate, a flexible substrate, and we would first print these metal interconnects. They're called electrodes here. It's technically, they're better called interconnects. And then we print the N-type semiconductors, and then the P-type semiconductors, heat and cure the thing. So we'd have a process which is relatively inexpensive, a 3-layer printing process which generates elements that are the length of which are controllable. So it looks like quite a promising approach. Here's how we do the printing. This is a dispenser printing. It's little more than a sophisticated syringe, which is driven by air pressure, controlled by a computer, so that it dispenses the contents of the syringe onto the substrate sitting on a stage which is temperature controlled and also has XY traversing mechanisms built into it, so we can print exactly the design that we want. Here's a photograph of the actual apparatus. The bits are fairly obvious. These are the typical needles we use for this syringe, which go down in size from 1 millimeter to 15 microns. So we have got quite a bit of, we can achieve quite low resolution, about 1 micron resolution with a 5 micron reproducibility. And the feature size is limited by the syringe tip size, this being the smallest one that's commercially available, but you could also make your own at even smaller diameters. So it's a relatively inexpensive piece of apparatus. I think we've got this thing together for about $10,000. Let me talk about thermoelectric materials. Everybody who talks about thermoelectric materials talks about this figure of merit, this ZT, which is made up of the Seebeck coefficient, which tells you how much voltage you get for a given temperature differential, the electrical conductivity, the absolute temperature, and the thermal conductivity. Obviously, you'd like the Seebeck coefficient to be as large as possible. You'd also like the electrical conductivity to be as high as possible, because when you start draining power from this thing, you don't want there to be a significant internal resistance. And you'd like the thermal conductivity to be as low as possible, because that means there is less dissipation of heat through this device, and therefore less tendency for the hot side to cool and the cool side to heat. And the best commercially available materials at room temperature have a ZT of the order of about 1. So let's look at how these various properties vary as we move from insulators to metals. So this is this curve here. Forget the numbers here. Those are courtesy of Bill Gates. This number here, this curve here, represents the electrical conductivity on a logarithmic scale here as we move from insulators to metals. This is quite obvious that the metals have the highest conductivity and the insulators have the lowest. What may be less well known to you is that the Seebeck coefficient drops as we move from insulators to metals. And as a consequence, ZT, which is the green curve, reaches its optimum in the region of semiconductors. Thermal conductivity tends to go up as the carrier concentration goes up. Thermal conductivity here is the movement of electrons, here it's the movement of phonons, but nevertheless that's a valid way of representing the fact that metals have too high thermal conductivity to give us a decent ZT. So that's an important reason for our using semiconductors. So let's look at some of the materials we might use. These are commercially available semiconductors. Bismuth telluride and antimony telluride are the materials that we have worked with, and their bulk ZTs are the order of about 1. Now, let's look at how we make our materials. So that, for example, if we're making bismuth telluride, we will ball mill bismuth and tellurium together to generate bismuth telluride. Here it says mechanically alloying. That's a bit of a misnomer because, of course, what we're generating is not an alloy but a compound. That's then mixed with an epoxy, and then that is dispenser printed in the way that I showed you a few moments ago onto a flexible substrate. So it's a relatively straightforward process. We need to characterize these materials fairly well, so we need the appropriate particle size range. Here I'm showing them dispersed in the polymer matrix within the ink of this dispenser printer. You recognize, I think, immediately that these particles have to be in contact if this device is going to work at all. So there's a percolation problem there, which you need to be aware of. Here's a plot of the volume percent versus particle size that we typically use in our inks. If we go to too large a particle size, we will clog the tip of our syringe. If we go to too small a particle size, these slurries, these mixtures of particles and epoxy, tend to become too viscous and we can no longer use them. So this is our optimum range, about 10 microns and below, and we typically use them at about 8 volume percent in our inks. Here are some micrographs, some material. I'm going to skip over that one to the next one immediately. So these are micrographs of the bismuth telluride, that's the N-type material, and the antimony telluride, that's the P-type material. And these are after processing, so some sintering of these materials has taken place. And that sintering is to our advantage because it's essential that there be a link from particle to particle in order for there to be any flow of holes or electrons. So what about the electrical conductivity of these materials of ours? This is the bulk value for antimony telluride, and these are the values which we get when we've simply printed these strips of semiconducting material, and you can see at this point we're well below the bulk value. However, when we sinter, we come to within an order of magnitude of the bulk value, so that's not too bad. If we look at the other element, the bismuth telluride, then unfortunately sintering doesn't help here, so we're more than an order of magnitude below the bulk conductivity. Nevertheless, we persist because we have an inexpensive process, so maybe we could just make more of these materials rather than trying to improve their properties. This is a plot of the Seebeck coefficient, and unfortunately sintering lowers the Seebeck coefficient somewhat, but not by an enormous amount, something about 50%. And what's amazing is even with that lowering, the Seebeck coefficient of our materials is above that of bulk antimony telluride for reasons which we don't understand at the moment. And if we turn to the other semiconductor material, the bismuth telluride, you can see that our Seebeck coefficient is very close to the bulk value. So things are looking fairly promising at this stage. So what happens when we print these devices? Well, here's an example of a thermoelectric generator printed on a flexible polyimide substrate. These elements, that you can see the scale there, 5 millimeters. These elements are 5 millimeters in length, and their cross sections are about 500 microns by about 120 microns. And we can print them for whatever length we want, but we've been working so far with the 10-couple device with delta T's across it of 5, 10, and 20 Kelvin. And if you look at the output from this device, it's not brilliant. So from the properties of the materials, you would have expected this kind of an output when we put everything together, reaching a maximum of about 0.9 microwatts. Not a lot of power. In fact, we get even less than that, a maximum of about 0.2 microwatts, which has probably got to do with some contact resistances which we are trying to eliminate. And that's for a delta T of 10K. If we look at different delta T's going up to 20K, then of course we get more power out of this thing. We get close to 1 microwatt. So an alternative we've examined is this one. So this is what we call a single couple device where we've used only one semiconductor material, and that happens to be the P-type, and this is the better material of the two in terms of its electrical conductivity, and we've simply printed then an interconnect from that end of the bismuth telluride strip to this end of the next bismuth telluride strip to see how this would work, and that's what it looks like there. And this is the device just before it's placed on this testing device. This is a cooled element and this is a heated element. So we would stretch this material across this gap here, measure the temperature differential across it and so on. And you can see that this actually works quite well, so that when we have a delta T across this thing of slightly over 20 Kelvin, we get 4 microwatts out of it, which is starting to get into the sort of range that we want. So you could see we can do our energy scavenging, our energy harvesting. Isn't that enough to power these ubiquitous micro devices for sensing of various sorts? And the answer is, unfortunately, not. And that's because of the way this radio in this thing functions. In fact, the whole thing functions. So a typical cycle might look something like this, and think of this time scale as perhaps being 1 second or 100 seconds or maybe even 100 minutes, depending upon what the application is. Sometimes you need to know things very frequently, sometimes only once every few minutes or maybe even every few hours. So there'll be a period when this device is gathering results. It's measuring a temperature, it's measuring a pressure, it's measuring the number of vehicles passing a point per hour or something of that nature. It's measuring a light intensity. It's measuring the number of people in the room. There'll be a period when it will want to get results, and typically it doesn't need to transmit those results all the time. So there's a brief period, which might be microseconds or milliseconds, when it does transmit that data using the radio, and for that there's a lot of power required, something of the order of a couple, 3 milliwatts. And then typically the device might go back to sleep for a while. Maybe a period now where it doesn't need to gather any results for a while, and at this stage it's consuming power of the order of microwatts rather than milliwatts. So it's easy to generate using thermoelectric generators or some other harvesting method the necessary power here, possibly even the necessary power here, but it's tough to generate this level of power. So we do need to store some energy, and there are a couple of ways of doing it that we've worked with. One is using electrochemical capacitors, which I don't have time to talk about, and the other is working with batteries, and the particular battery we've chosen to work with is a zinc polymer battery. So this guy provides the power, and this provides the energy, loosely speaking. This has a high power per unit area. This has a high energy per unit area. And typically, we might have a hybrid arrangement between these two, but let's not worry about those details. Why zinc? Let's look at this chart over here. This is all theoretical energy density, which actually doesn't mean a great deal when it comes down to building a practical battery. But nevertheless, it's an instructive place to start. So if you build a zinc air battery, then in theory, it's got a very high energy density of the order of 1,000 watt-hours per kilogram. And that's far greater, say, than the lithium-ion battery, which probably powers your laptop. Now, if we look at our particular battery, zinc manganese dioxide, you could see it's not quite as good on this theoretical energy scale as lithium-ion, but it's pretty damn close enough for us to consider this to be a practical material, practical couple to be using in a battery. It has the advantage of electrochemical reversibility, so we can reverse the reaction to store energy. Compatible with numerous electrolytes. The materials are relatively low cost. Zinc is far cheaper than lithium, for example. Our manufacturing costs should be low, as you'll see in a few moments, and it's easily recycled, less so with lithium. So that's our choice as one of our electrode materials. But zinc is notorious. I realize I've left my cell phone on, so please excuse me a second while I turn this off. Zinc is notorious as an electrode for being unsuitable. And it's unsuitable for two reasons. One is that it forms these ugly things called dendrites. So this is like a fern, if you will, but unfortunately it's rigid. And as you'll see in a few moments, if these things grow in your battery, then you have serious problems. And so there are no commercial systems using no commercial rechargeable systems using zinc at the moment. Another problem is illustrated down here. Incidentally, these are all investigations by other people, not ours, these results at least. This rectangle was initially completely covered with zinc. It was part of the battery. And it was cycled, charged and discharged, in other words, 280 times, and looks what happens to the zinc. It migrates from being a uniform distribution all over this plate to being clumped in the middle in this thing which looks like the X-ray of the skull. So how could we, to elaborate on this problem with the alkaline systems, this is the alkaline aqueous systems, alkaline aqueous electrolytes. So during discharge, the oxidation of the zinc forms zincate ions, and these diffuse throughout the battery. So when you come to recharge, they'll come down just about anywhere they want to, anywhere there's electrical contact at least. So this causes this size and shape change that you saw in the previous slide. And another complication is that at high zincate concentrations, zinc oxide precipitates, and that's a non-conductor. If you get that over your electrodes, you will essentially passivate the electrode. So there isn't a good history of using zinc electrodes, at least with aqueous electrolytes. But what about changing the oxidation state, the oxidation reaction, by using ionic liquids instead? So we're going to move away from aqueous reactions, where this is the principal reaction that occurs during discharge of the zinc. So what are these ionic liquids? Best way of describing them is that they are molten salts. Think of molten sodium chloride, for example. It's only got two species present, approximately. It's got sodium ions and it's got chlorine ions. That's different from a solution of sodium chloride in water, which has got water molecules there as well. So this is not an organic species in a solution, although we do put these in solution for processing purposes, but it's something that is liquid at room temperature, but it only contains two species, an anion and a cation, just like a molten salt does. And one of them, either the cation in this case or the anion in this case, are these complex organic molecules. And it's because we have these huge, complicated molecules that the thing will not solidify. There's, if you will, a steric hindrance to the solidification. So that's why it's liquid at room temperature in some cases, certainly below 100 degrees Celsius. And there's some more details here which we would needn't worry about. But they have very low vapor pressure. Typically, they're hydrophobic, so they don't pick up water, which is a nice thing to avoid if you have an electrolyte in a battery. And very important here, they have a high electrochemical stability. So over a range of about 4 volts, they will not decompose. So those characteristics make these ionic liquids very suitable for the kinds of batteries that we have in mind. So here's an example of one of our printed batteries. So this is a layer of zinc particles separated by a gel, which is essentially one of these ionic liquids in a porous polymer matrix. And then here's the manganese dioxide. And you can see that this is only about 100 microns thick, and that's about the thickness of a human hair. And this was printed by the system, the dispenser printer system you saw in the previous few slides. And so I'll bring your attention to this little table down here. You could see an energy density here of 130 watt-hours per kilogram. That's not a bad performance. A good lithium-ion battery might be up to about 150, 160 watt-hours per kilogram. So we're quite close. And what's also important is we can pack a lot of energy into a square centimeter. And I'll use that number later in my presentation. What's also intriguing is that by using these liquid ion electrolytes, we can substantially enhance the lifetime of this battery. So this particular battery was cycled up to about 80 times without any loss of its capacity. If this had been an aqueous electrolyte, it would have gone, it would have ceased to function after about 5 or 6 cycles. So the introduction of this ionic liquid in this gel enables us to achieve very high cycle lives. And that's part of the secret sauce of this printing of batteries. We're therefore very interested in the development of microstructures on electrodes, and here's the tool we're using to do that. It consists of this diamond-shaped electrode here facing a strip of electrode there, and this is done under a microscope. So this is a microscope slide, and this is a microscope cover glass, and there's a blob of electrolyte there. And this is a not very high magnification optical micrograph of the two electrodes, this one on the left and this one on the right. And you'll see what happens in the next slide. So these are, if it all works, movies of what we see. So that was the diamond-shaped electrode on the left-hand side. And as this movie proceeds, you'll see eventually the other electrode coming into view. You could see we've already started to form some of these nasty dendrites here at the tip of this diamond-shaped electrode. These things here, incidentally, are gas bubbles which form if you use too high a current in this device. So if I click on this, I should be able to make it play. Okay, there we go. So you could see these nasty dendrites evolving here, and eventually they stretch all the way over to the counter electrode. And at this point, you've shorted out this cell. It's no longer functioning as an electrochemical cell. Any flow of electricity is strictly through these chains of of zinc to the counter electrode. Over on the other side of this picture, I have a slightly different movie, which shows something called a mossy zinc deposit being formed. So you see it's not quite as dendritic, but it's still quite an ugly deposit. We would like this deposit to be uniform all over the electrode. That's in aqueous systems. The obvious question is what happens when you do this with a liquid ion electrolyte, and I confess we have not yet done that, although I do have a couple of micrographs to show you in a moment. So, God willing, I can move on at this point. Let me try something different. There we go. So, here are some micrographs from our lab. This is zinc deposited at low currents. As we go to higher currents, it becomes more irregular, and at the very highest currents, we develop these nasty dendrites. So we're spending quite a bit of effort looking at the microstructure of the zinc that is deposited when we work with these various electrolytes. Here's an example of the structure which develops when we use one of these ionic liquids. And you can see it looks very different from the micrographs of the previous slide where we were using an aqueous electrolyte. And this is an enlarged view over to the right here. I'm hopeful that my optimism tells me that this structure is fragile and is therefore got zero ability to punch through our gel electrolyte to short out the cell. So, but we'll see about that as we go forward. Now I want to finish up by talking about a much larger scale. So we've been storing energy in the previous many slides for devices which are small. Now let's think about storing energy for your house, which might have solar panels sitting on the roof. And for that, we need to store about 20 kilowatt hours of energy to cope with nights or with periods of bad weather and so on. If you think about a wind farm, to take care of the situation when the wind doesn't blow, you need about 100 megawatt hours of storage. And the question arises, can we print this level of storage? Well, possibly we can, and I want to show you a couple of printers which are larger than a dispenser printer. So here's a screen printer, a sophisticated version rather than the $20 version you can buy in Kmart to print a shirt or something. So that's one scale up. Another scale up would be to this thing called a flexographic printer, which, as you can see probably looking around here, is a common device for printing things that are like labels, or that are 10 centimeters by 10 centimeters, let's say. I want to remind you that printing has been around a long time. So in 1439, Gutenberg invented the printing press. So we know a lot about how to do printing. It's an enormous industry, unfortunately shrinking, of course, because we don't read newspapers anymore. And the notion is, can we use our chemistry and inks and know-how that we've developed at the dispenser printer level to work with, say, one of these guys to produce things on a much grander scale, which might be suitable for storing energy for a solar installation or a wind farm. I want to convince you that printing is moving beyond making newspapers and so on. So coincidentally, there are 3 publications that have appeared recently. There's something out of the Palo Alto Research Center, one of their house magazines, about them being ready to print electronics. The January issue of The Economist had solid-state batteries, power of the press, talking about printing batteries. Unfortunately, they forgot to mention us, but that's all right. They will in the future. And here's a recent article from last month's issue, an issue in last month of The Economist, talking about the 3D printing, the printed world. So printing is not just for newspapers, wallpaper, and labels anymore. And another good example is nano solar. As you're probably aware, this company is making solar panels by printing. And they're doing that at about 100 feet per minute. And I won't dwell on the details of this, but they're obviously making a success of this, which is very encouraging. So why is printing better? Or why are we doing printing? A simpler and cheaper way of manufacturing things than traditional microfabrication. So if you look at a typical microfabrication, you pre-process, you deposit a film, you deposit a photoresist, you expose the photoresist through a mask to some light, you develop the photoresist, you do some etching, you remove the photoresist, you do some sort of post-processing, then you start all over again to develop the next layer. So it's a very lengthy process. You have to repeat about 5 times. Over here we have this printing technology that we've been working on. Incidentally, this is the logo of a spin-off company, a small Berkeley company, formed by one of my former graduate students, Dr. Christine Ho, and a colleague. So here we can just simply print what we need. So it's an additive process rather than a subtractive process that we have over here. So as a consequence, the materials costs are very much less. And I want to convince you in a few moments that the printing costs can be as low as 10 cents a watt hour of energy storage. Whereas the typical battery that's printed in this way might be well over $1 per watt hour of storage. So let's move on to that. Piedmont Post is a local paper, and they were kind enough to tell me how much it costs them to print. This is a small run, of course, only 2,200 copies of a paper which has 36 pages, including 4 that are color, and their printing cost is only $1,600. What does that work out at? Well, that's 15.8 cents a square meter. So if I add the cost of the chemicals bought in bulk that I need for the battery, the zinc powder is going to cost me 65 cents a square meter. The MnO2 is going to cost me 26. The organics are going to cost about 45 cents a square meter for a total of about $1.52 per square meter, everything included. A square meter of our zinc ionic liquid manganese dioxide battery can store 15 watt-hours of energy, and therefore you do the simple arithmetic, and the energy storage capital cost is approximately $100 per kilowatt-hour stored capacity, which is a very nice figure. So if I look at what the rival technologies cost, we're right there in the middle of the competition. So this is capital cost. This is how much it costs you to buy a system to store energy. It's not the operating cost, it's just the capital cost. So this is the capital cost per unit of energy stored, and this is the capital cost per unit of power. So you can see that the cheapest in terms of both those capital costs is compressed air energy storage, but that's not got a brilliant future. Nobody wants this thing in their backyard. Pumped hydro is a possibility, but again, you don't want to do that in the Sierras. Metal air batteries are a possibility. But the most popular one for large-scale energy storage right now is sodium sulfur, and you can see that our projected capital cost is right there in that ballpark. These are flow batteries, by the way, zinc air, lithium ion, long-duration flywheels, high-power flywheels, and so on. So we believe we have a very economic way of storing energy. What are the problems when we want to do this scale-up? I'll point out just 1 or 2 of these. Thermal management. So thermal management is no problem when you're talking about something that's a few centimeters by a few centimeters. But if you're talking about things that are a meter by a meter and probably a few centimeters thick, then how you manage the temperature of this device when it's heating up internally becomes a significant issue. We have to think about printing and curing, as you'll see in a few moments, so that if we're printing, say with a flexographic printer, which is one of these roll printing devices, I'm showing 3 printing stations here. Actually, there will be 5. You want to lay down something called a current collector, then you print the anode, then you print the electrolyte, then you print the cathode. But you have to be careful that by the time the anode material has gone from here over to this print station, it's dried. Because if it doesn't, you'll smudge everything, right? And in this case, smudging is not just an aesthetic problem. It is a problem that the battery won't work. So you need some drying, probably by infrared heating, maybe by applying a vacuum at this stage, at all stages between the print stations. So that's something we need to address as we move forward. So coming up on my final 2 slides here. So dispenser printing seems to work for printing TEGs, thermoelectric generators, batteries, and capacitors, and we've done all that. It's a very flexible tool. We can print batteries just about where we want them. We can put them anywhere we want, for example, on a printed circuit board. which has certain advantages which we don't have time to go into. The future work we're going to do will include research on improved thermoelectric materials, zinc gel electrolyte interface, improving cycle life of batteries, and improving the performance of capacitors. And I hope I've given you a glimpse that large-scale printed energy storage is a possibility and will lead to energy storage which is relatively inexpensive compared to some other technologies. So my acknowledgement here, besides all the wonderful students and my colleague Paul Wright, I'd like to acknowledge the California Energy Commission that has supported this work, and I'd be happy to answer any questions, and if you want to send me something by email, there is my relatively easy to remember email address. So thanks for your attention.
Thank you, Jim. Let's open the floor for questions. Got one in the back.
No difficult questions, please.
One would guess that thermoelectric generators would probably be in high-temperature environments, which might be incompatible with other circuitry, like either the batteries or capacitors or semiconductors. And so I'm wondering, I suppose you would have them separately located with a long wire between them, or how do you envision that these thermoelectric generators might be configured?
Well, let me give you a little personal experience. When I let me go to enlarge it slightly by going to slide view. So this is an aluminum plant here. The inside of these electrolytic cells here is at 960 degrees Celsius. And we have powered wireless devices by placing thermoelectric generators on the outside of these things, where temperatures are of the order of about 100, 150 degrees. Now, those are not our thermoelectric generators. They are commercially available ones. For this application, we're not interested in having things that are tiny, for example. So, yes, it's a consideration. And I think if one or two of my next slides, if I can go there. Sorry, I'm going the wrong direction here. You can see the temperature range over, well, I won't bother to find it, but if you, there are various semiconductors which are suitable for various temperature ranges. So I couldn't imagine using these things above 400 or 500 degrees, for example. But as long as we stay to within a couple of hundred degrees, then they'll work fairly well. Have I answered your question?
Yeah. What's the difference between your technology and Alphabet? That's a company that's doing that, licensing their technology for thermal generators from the lab up the hill. Do you know anything about that company?
I know very little about that company. There was a seminar yesterday in my department given by somebody from Alphabet, and I confess I wasn't there. So I don't think they're printing their devices.
No, I don't think so. I think it's a semiconductor type of material.
I think they have an improved material, right.
And it's licensed from the lab. The other question I had for you was, how do you compare with flow batteries like zinc bromide, for storage?
Okay, let me see if I can't find that slide. So those are flow batteries there. And I think most of that data is for vanadium flow batteries. I don't know the company. There's been a lot of work at University of New South Wales, and there's a spin-off company from there which has generated a lot of data in this area. In fact, I think I plagiarized this slide from one of their presentations. Yeah, sorry, that's flow. They're flow batteries. Yeah, and all these are estimates. I mean, some of these things are including our own, are at a fairly early stage of development. The only thing that's really huge at the moment is sodium sulfur. So I believe PG&E is building a large sodium sulfur storage facility somewhere in California with California Energy Commission funding.
We have a question from the back, Jason.
Sure.
So does this slide take into account the amount of time that the battery can be charged before it degrades?
No, this is an initial cost.
Okay.
And That's an important consideration. Now, I think you would regard that, well, maybe you do regard it as a capital cost, but this slide says nothing about operating costs.
Okay. Thank you.
Any more questions? Okay, we're good. Okay. Thank you very much, Jim.